In this video lessons, I like to discuss the voyage optimization due to severe weather condition, and especially the voyage optimization on routes between the North Continent and the east coast of the United States, meaning crossing the North Atlantic, especially in wintertime. The optimization is focusing on the wave height and roll resonances for high wave or high wave impact. The ship, what I will use as an example, is a 4,400 TEU ship, and on the voyage from North Continent to the east coast of the United States. Especially for this container ship, it's very important to see if ships are really running into roll resonance areas or not, and what type of roll resonances we are facing if we are in roll resonances. That can be already foreseen by using also programs or by do it manual to prepare a roll resonance diagram. And we are focusing also on the high waves and the impact of high waves for such voyages. So then let's start. That is our weather chart, which is actually a weather chart represented from the 1st to the 6th of January 2022. We can see here that we have a very huge low pressure, which is moving here to the North Continent. As we said, the type of ship is a container ship, 4,400 TEU. You are 90% loaded. A windage area for this container ship is, for this type of cargo loaded, is 4,760 square meters. For the wind load for this condition, we will have a wind load of 114 tons for this area of 5,760 square meters. The planned speed is 15.5 for the intended voyage. The natural rolling period for the GM is calculated with 20 seconds, and the wave period is about 8 seconds. So let us see, that is actually my planned route. That means the black line represents the original and planned route for the voyage from the North Continent to the east coast of the United States. Time of the voyage is here January, and the blue dotted one, which are here, represents later on two positions, which means the 48-hour and the 24-hour condition. So let's see if my ship will be here at this condition, or at this position. What will be the influence, or what might be, where will I be influenced? So that is my position. So we can see that at this position I have wave and wind direction from around about 190 degrees with 35 knots. So we could actually assume that the ship will come into synchronous rolling because we have very high wave beam waves as well, and that is always a guarantee that the ship, or might be a guarantee that the ship comes into parametric rolling. But therefore we have to check this. So by using a program, and this is here error, what we are using to find out if there is any roll resonance area the ship will face. So here we can see that is now the plot for this situation. And we see that is my course, that is my wind direction, and this is actually the areas. And we can see that the area is really like a butterfly because we have wind sea, and wind sea is not like a constant swell. So it's more diffusing. So which means I have, instead of this synchronic rolling area, instead of 30 degrees each side, let's calculate with 40 degrees each side, and then we are coming to such a diagram. Here we see parametric rolling, and this is following C, where the ship is for sure not in. But we clearly can see, even if it on a glance looks like that my ship might face roll resonances here, the ship is not in roll resonance, not here. So this is the 48-hour position, and we have the same here as well. Prepared the roll resonance diagram, what you normally should do in the moment we are only focusing on it. And we can see that also here, this is my wave direction. This is the synchronous rolling, that is parametric rolling, and that is actually my following C is not be real problem, because actually the ship is not encountering any of these raw resonance areas, so, and has actually no problem with this. But what is the problem here? We can say that at the end of the day, the ship is not affected by raw resonance, but by wave heights, because the wave heights are between 6 and 8 meters. That means huge wave resistance and therefore speed to be reduced. Only for the raw resonance diagram, for the positions what we had already, the ship will be not affected. The disadvantage is the wave resistance, which causes the ship speed to be reduced, and with wave heights of 6 to 8 meters, the speed must be anyhow reduced to avoid damage to ship and cargo. Therefore, we will also be late. That means I cannot keep my ETA. And somewhere on this route here, I have to increase my speed. That means we have a more consumption again. So therefore, if we would now optimize directly here, if I'm out of the English Channel here and then coming into the Gulf of Biscay, going more southerly route, we will see that here that is from the weather situation, the more suitable and better route than the northern route here. Why? Because here we will not face, on this route here, we will not face such high waves like we have this here on this route. And therefore also the ship's wave resistance is here by far or drastically reduced and by far less than on the northern route. And we can see here that normally here we have a good run, and we can keep and maintain also here, if we have it in a charter party, the good weather clause. Here for this route, the good weather clause is mostly not calculatable because I have always above Beaufort 4. And this is also the better route because I can presume that there will be no damages to ship and cargo. The optimization route will present a better weather condition, and also the wave height is drastically reduced, as we said, compared to the northern route. Therefore, the speed can be maintained and the ETA can be kept. No additional fuel consumption. Also, the speed warranty can be fulfilled if we're saving the southern route. And so that is an important fact. If we are optimizing, we are not only optimizing to the wave height or to the wind speed, then we are optimizing also to maintain the warranties given in the charter party, which is one of the parts if we optimizing a route. So here we can see that we have at the beginning maybe 3 meters, but later on we have 1 to 1.5 meter wave height. Therefore, the ship is resistant. That means the wave resistant by far less compared to the northern route. And this actually is also why we have to use the voyage optimization to fulfill requirements and to avoid damages to ship and cargo. This example is a very good example to explain what is required for us to do. And at the first glance, we say, or we have seen that the ship is not affected by raw resonances, even if it looks like, but it's not affected by these raw resonances. So that is an important fact. So we can never say, if we are sailing this route, the ship will be affected in the first glance by raw resonances if we are not able to prove it. And what is here done by the program, you will get out the same if you do the manual calculation using a radar plotting sheet. So here the optimization is to the wave height, and to reduce the wave height, therefore to reduce the wave resistance, and therefore I can keep my speed and I will also keep my ETA without drastic fuel oil consumption. Okay, that's it to have a practical approach in optimization of a route due to weather condition. Thank you for watching this video.